Hey everyone, we're going to have a look at digital audio. And I guess to get started, it's important to kind of understand that, when we're thinking about analog signal flow and how all of these components go, or how this audio goes from one component to another, that there is certainly a digital representation there, or in the digital world, there's a representation that we need to understand. And to truly understand what's going on, you need to know kind of the basics of digital audio. Now, I know that this will be some review, especially the first half of this lecture. But towards the second half, there's going to be some new things that mostly deal with how we interconnect digital audio devices, which again is real important back to that idea of signal flow, how audio flows from one point to another, where it goes from the analog to the digital and back again, and then how we might transfer information from one digital medium to another. These are all important elements because every part of the process could degrade our audio if not appropriately connected, and other particular details that we'll talk about as we go along here. So let's go ahead and get started. Some things that you should be comfortable with, and some things that you probably have heard in the past, is that when we're talking about the quality of a digital recording, there's really two basic principles that we have to understand, and that is sample rate and bit depth. With these two things, that's what forms the quality of the overall recording. How, I don't know if you want to say how good it sounds, but certainly the frequencies that it can record and the volume that it can record. And those ultimately are what going to make up the quality of our audio. So one thing that I want you to be comfortable with is this acronym. It's PCM audio, pulse code modulation. When we talk about a WAV file is actually just a package that contains PCM audio and then perhaps other information like we might call it metadata, which might be when you put a disk or an MP3. Well, it wouldn't be an MP3 in this case, but a WAV file playing on your computer. It has the ability to show you text of what the audio is that you're listening to. That's metadata, and some other information might get stored in there as well. But the PCM, the pulse code modulation, is the idea where an analog waveform that gets inputted into an A to D converter, an analog to digital converter, is going to have pictures taken of it. And that is how often that happens is the sample rate, and then the bit depth is a coding of the value of each of those samples. That whole concept of quality of digital recording, sample rate, bit depth, is called pulse code modulation. It's been used for years and years since the advent of digital audio. And there's been a couple other options out there for encoding into the digital world, but PCM audio certainly has been at the forefront of the methods and standards that we use for most of our audio recordings in the digital world. So again, just a kind of an overview. Samples, a representation of a snapshot at a single point in time, almost like if you think of it in the visual world. The frames of a film would be a single frame would be similar or analogous to a sample. And then the sample rate is how many times a sample is actually taken over a period of time. And it's defined in 1 second. And we know that in cycles per second, that's measured in hertz. So sample rate is actually measured in hertz as well, which we'll get to here in a moment. But you can see here in this diagram that if we have a low sample rate, there are less snapshots. That if you look at the original waveform and then look at the snapshots that are taken at the top, the fewer snapshots, I actually use the mouse here, fewer snapshots, if we were to just visualize what that's going to be, it's not going to be as accurate of an example. Like, for example, the A to D converter wouldn't know that this audio actually kind of dips down here and then shows up at this sample. But the more samples we take, the better representation, where here you can see that, oh yeah, we're now representing the fact that that sample is dipping down and gives us a truer form of the analog signal. It's also important to understand that analog or digital will never be analog. In other words, you could zoom in to the nth degree and still see the stair step, or you can see that there are still samples that you could take to represent that original analog format. And for that reason, analog, in my hope, will never die. I mean, there's certainly a lot of advantages to the digital world, but digital will never be analog. They can get pretty darn close, though, these days. And the benefits sometimes, to many people, outweigh the negative impacts of the fact that it's not the true analog of the analog signal. So it's important to understand this concept, the Nyquist theory. And again, I'm certain that you've covered this in the past, but the idea of the Nyquist theory is that the sample rate must be twice that of the highest frequency to be recorded. So if we wanted to record the highest frequency that we can hear, so 20K, we want to hear that we want that frequency to be recorded, then the Nyquist theory states that we would have to record at a sample rate of 40,000 times per second. And again, we're measuring this in hertz, so 40,000 hertz. Now, the biggest reason that we need it to be twice that is because, let me step back here. The reason we need it to be twice that is because we need there to be at least two samples for a waveform to show us the peaks and the troughs of that waveform. So if the highest frequency is 20K, then we need at least two samples for that highest frequency, the peak and the trough of a 20 kilohertz sound, in order to sample that accurately. And then the A to D converter kind of fills in the gaps of that sound, which is terrific for us to reproduce that. So what we end up with then for a sample rate of our CD is 44.1K. And so the highest frequency that we could record at that is 22,050. So that kind of seems odd. Like, why did we choose that particular frequency? Why isn't the sample rate, just straight up 40K, because we can hear to 20? And it all comes down to this idea of aliasing, where if the A to D converter hears sounds above that Nyquist frequency or hears sounds above 20K, which it will, it's possible that you might have a microphone that can capture sounds above that. Well, when those samples are taken at a lower sampling rate, so if we're only sampling at the ability to record 20K, but the A to D converter is hearing 24K, then we have problems, and it's called aliasing, where we actually end up hearing sounds within our frequency spectrum that are not the real sounds. They're aliases, but they are in fact sounds that we can hear, and that to us is bad. We are introducing new sounds into our audio, and at 40,000 times per second, those little snippets of audio become distortion. So we're not talking about like long sine wave tones or anything that we hear down in our audio frequency. We're hearing just very small little snippets of this audio, but it's happening very fast, so it ends up being very random distortion, and that is never good. Well, sometimes distortion is good. In the analog world, it's a pretty hip thing. So how do we combat that? Well, we combat that with an anti-aliasing filter. Well, a filter, as we know it, would be a high-cut filter in this case, or a low-pass filter. And that thing is set as an input into the digital converter, so that way no frequencies above a certain frequency can even be heard by the digital converter. And this is a great thing, because then if there is audio up in the stratosphere, maybe let's say 24,000 hertz, that is trying to get into that analog to digital converter, the filter just says, nope, you're not getting in there. It's not going to be converted into digital. Well, that filter, the filter slope, how steep the slope is really what causes us to have to move into this 44.1 sample rate, because we don't have this just this perfect exact cut off filter. It's going to have a bit of a slope to it. So we move the filter up to 20,000. The frequency would be at 20,000, and then it gently slopes down into this 22.50 hertz. So, we said everything pretty much above 20,000, we don't necessarily need to record for our human hearing. So between the 20 and 22 0.5 kilohertz frequency, it's actually the anti-aliasing filter is actually slowly filtering all of that out. So it's a long discussion on anti-aliasing filters. There's certainly more to understand about it, but that's kind of where we came up with this really odd number of 44.1K for our CDs. Now, should we record at higher sample rates? Are there sounds above 20,000 that are there? Yeah, absolutely. And then you get into kind of like psychoacoustics, and the idea of a piano is a great example where, the piano has fundamental sounds or the notes that we hear, but the true sound of a piano, the timbre of a piano, what makes each piano unique is the overtones and the harmonics that you hear in that sound. And there are overtones above our range of hearing that provide a level of detail to the sound that it's a situation where when they're not there, you know it. When they are there, you get that truer sense of realism. And we have great examples of when they're not there, and that's like digitally sampled keyboards when they're trying to sample a piano, and we can just say to ourselves, that doesn't sound like a real piano. Well, a lot of times that has to do with the fact that that real piano was sampled at a lower sample rate, maybe to save space, conserve space, that sort of thing. Well, those frequencies do exist up there, so why don't we just record them at a higher sample rates? Why aren't CDs at a higher sample rate since they exist and we can get a truer realism of the sounds? Well, that's because for the longest time, CDs were the standard, and the millions and millions of CD players that were sold and put into computers and in car stereos and that sort of thing, you actually would have to have a different laser and a different player to play and reproduce 48K samples or something, at a higher sample rate. So it kind of just came down to the consumer level where 44.1 was pretty good. Most people were okay with that sampling rate. The quality was pretty amazing. And moving up from there really wasn't necessary for your average everyday listening needs. That's not me talking. That's the consumer, in quotes, talking. So that's the idea why CDs kind of just stayed at that lower sampling rate, even though we do have the ability to record at higher sample rates. Now, DVDs, DAT players, digital audio tape, kind of an old technology, those recorded at 48K. So those had the ability to record up to 24,000 hertz. Gives you a little bit of better or higher frequencies that you can record. This is a DAT player. Back in the day when I was working at a studio, we had probably, 20 of these. I mean, this was our method of bouncing to disc when you had to record down to a DAT. It's like a little mini DV tape that you slid into this tray, and it recorded in stereo, but it recorded the digital information to tape-based medium, and really robust machines. But again, CD burners started to take over, and then, of course, recording or bouncing straight to your hard drive is ultimately the method that won out for recording this digital audio. So we don't see these around too much, but that idea of audio for video recorded at 48K at a minimum is very typical. Other sampling rates that you might find would be 88.2, 96K, and 192. So if you think about 192K sampling rate, that means that we could record frequencies up to 96 kilohertz. The sound would be up to 96 kilohertz in the frequency range. That's catastrophic. I mean, it's huge. It's really, really high up there. But the level of realism and detail is unbelievable. Now, for certain genres of music, it might not be necessary. And I hate to clump them all together, but maybe in the rock genre, we don't necessarily need to hear that clarity of all of those instruments quite as well as perhaps an orchestral recording or a solo vocalist or maybe a jazz trio or something like that. And that's where you find a lot of these high sample rates at 96 and 192 being used in more of the orchestral recordings where you're getting a level of detail and from the musicians there. All right, so just to recap, higher sample rates will provide higher frequencies. So if I record at 48K, I can record up to 24,000 hertz. If I record at 192K sample rate, I can record up to 96 kilohertz in the frequency. When we move to bit depth then assigns a value to each of the samples that are taken. And as we increase the bit depth, we get to increase our dynamic range. And so ultimately, frequency and dynamic range are the two main components of audio that we're trying to capture. So every time that we record a sample, each of those samples is given a binary number. The ADC, analog to digital converter, is what that stands for. And every time that is assigned a number, it's called quantization. So you can see here on this graph that, when a sample is taken right here, that the A to D converter assigns that sample a number, and in this case it's a 16-bit word, and that particular bit depth is assigned a voltage. Well, that voltage is how we recreate the sound back in the digital to analog conversion. When the digital converter spits out that number, it spits out the 0.876 volts, which moves the speaker that much. And imagine this happening 44.1 thousand times per second. That speaker's moving fast at different voltages, and that's how we're moving that air pressure to recreate the sounds from this digital information. So this graph is representing this concept called quantization errors, where if we don't have enough bits, so let's say in this example we have a 3-bit word. I mean, that's really weird. We never really record anything at 3 bits. Probably the lowest you've ever heard of is recording something at 8-bit. But 3-bit gives you a good representation where we have an analog sine wave, one cycle that's trying to be sampled, and you see there the dots is wherever all the samples are being taken. But the problem is that when we try to quantize that, this sample right here, when we try to assign a value, it gets caught in between. It's either going to quantize to this number or this number. It can't be right in the middle because there's literally no bit to represent that. So what happens is that we get this kind of tick, and you can see down here, these tiny little ticks and pops are these quantization errors where it has to round off because the bit depth isn't high enough to represent the audio. Well, these tiny little ticks, again, are happening at 44.1 thousand times per second, so we don't hear them as like tick, pop, pop, tick, tick. We hear it as distortion, and it's very random distortion. So that random distortion just ends up being like noise, or if you've heard of, in the analog world, tape hiss, that would be kind of represented by that sound. And that's, again, called quantization noise. So I'm going to take a drink real quick. So let me switch over here real quick and let you hear quantization noise. So again, the idea here is that the more bits that we have, in case of a CD, we record at 16-bit, there are a huge amount of values to use for, and I think I actually have that number written down here somewhere. Let me escape. I have it in my notes down here. I always like to use these. Maybe I don't. Yeah, here you go. Yeah, check this out. I always have to refer to this. I never committed this to memory because all I know is that 16 bits, a huge difference in values. I mean, if I record at 16-bit, I get 65 levels of velocity for a sound. I mean, that's a lot, 65,000 values. But look what happens if I move up to a 24-bit. I get 140 dB of dynamic range and 16 millions of values of velocity. So the kind of representation of dynamics at a 24-bit is exponentially better than 16-bit. It's kind of interesting that we use 16-bit for our CDs, CD quality. 24-bit though is certainly or 24-bit is certainly a better way to go if you have the ability to do that. All right, so let me show you here real quick a quantization error example where we have this Radiohead song that slowly progresses or decreases from 16-bit down to 1 bit. Let's see if you can hear this. So we're starting off at 16-bit audio. Eight-bit, you hear a little noise.
The breath of the morning, I keep forgetting. The smell of
4-bit.
the warm summer air. I live in a town
2-bit.
can't smell a thing. You watch your feet, the crowd.
1. So what's interesting there at that 1-bit is you think about it, it's only there's only two options, on or off, when you come to that 1-bit. So if that audio is above a certain level, it gets rounded up to the on position. If it's below a certain level, it gets rounded down to the off position. That's why you only hear these ticks. So of course, that's why we don't record anything at 1-bit. 16-bit, the noise that we heard, that quantization noise, was really low, so low that we really couldn't hear it. The quality sounded fine. 8-bit, we heard that noise get a little bit louder because there's more rounding off. 4-bit, we can hear it's really distorted. So hopefully that gives you an understanding why bit depth is really important, and also gives us that level of dynamic range, higher level of dynamic range. So again, at 24-bit, we get 144 dB of dynamic range. It's 16 million velocity levels that we get to record. So when I do a recording, multi-track recording, I am typically recording at 48K 24-bit. That is a standard that I have used for in my recording experiences. Some people choose 44 124-bit. Some choose the 88.2 24-bit because when converting to CD, the math works out quite well from going from 88.2 to 44.1. So just differences of usage as you go along. Now, there's a way that you can mask that noise when converting from a higher sample rate to a lower sample rate. So if I were to record a multi-track session at 48K 24-bit, eventually if I want it on CD, it's got to go down to 44.1 16-bit. Well, that 48 or 24-bit to 16-bit, literally chopping off 8 bits of audio. And that 8 bits of audio is really very soft sounds in the audio. So to mask the noise that gets introduced when we're moving from 24-bit to 16-bit, we can apply more noise. Kind of seems backwards, but quantization errors are very random noise. And if we mask that random noise with more consistent noise, again, these oxymoron type of terms I'm using, consistent noise would be like white noise or pink noise. And if we mask that sound, it's a little bit more pleasing to our ears, moving from 24-bit to 16-bit. And we're talking really, really soft noise that sometimes you wouldn't even know that it's there. Kind of a quick aside, vinyl records, if you were to translate vinyl and the amount of noise that was involved in vinyl, that would only be 13-bit audio. And so moving to 16-bit, that's pretty good to begin with. Going to 24-bit, that noise floor, that quantization noise is really, really, really soft. You'd have to amplify the signal quite a bit in order to hear that noise anyways. But just kind of as a safety net, when we're going from 24-bit to 16-bit, for that conversion, we would apply dither. It's about all I'm going to say about it right now, because when we talk about mastering, which is where dither really comes into play, we'll discuss that more.